Welcome back, everybody, to the continuation of the preliminary example. We're going to be looking at part B, and this is still page 38 of the workbook that we're looking at. Okay, let's read this problem together. So, approximately how fast does the temperature change at the point P equals 1, 1 as you move toward the point Q equals 1.66, 0.5? Okay, so I want to scroll back up to the picture so that we can visualize what they're asking us here. Okay, and I'm going to start by looking at the contour plot. Okay, you can see the P and the Q here and here, and we're trying to estimate the rate of change of our temperature as we move between those 2 points, from P to Q, like that. Okay, now the first thing I want to emphasize before we dive into this is that this is a new problem here. We haven't done a problem like this before. If I had asked you, find the rate of change away from P in the x direction or the y direction, we could have answered that. That would be just asking you to evaluate the partial derivative. But here, we're not moving in either the x or the y direction. We're kind of moving in between the x and the y direction. Okay, so how do we do that? How do we estimate that rate of change? Okay, well, one way is just to kind of go back to concepts here. Okay, so the rate of change of the temperature kind of a quick way of estimating it is just to ask, okay, how much does our temperature change? That would be the change in F. And then just dividing by the distance that we traveled. Okay, the length of the vector from P to Q. We're just kind of using a basic rise over run type of approach here. All right, well, how much does the temperature change? Okay, and I apologize for the scrolling, but we're going to kind of need to scroll up and down. Okay, so when we move from P to Q, we're going between 2 contours, and notice that we start at 0.5 and end at 0.25, so that's a temperature drop. Okay, the difference in temperature would be 0.25 minus 0.5. Okay, we want to divide that by the distance that we traveled, so that's going to be finding the distance between P and Q. There we can just use the distance formula. Okay, so 1.66 minus 1, that's going to be 0.66 squared. And then 0.5 minus 1 is going to be minus 0.5 squared. All right, and then we'd go ahead and just get a number for that. Okay, and actually, I think I'm going to include a little bit more detail in this calculation. I don't want to confuse anybody here. So the distance between these 2 points, we're really taking the differences between the coordinates. Okay, so it would be the square root of 1.66 minus 1 squared. That's where that 0.6 came from, plus 0.5 minus 1 squared. Okay, and just write out a little bit more detail there. Okay, and at this point, job for your calculator, so you could go ahead and punch those numbers into your calculator, and what you're going to come up with is an answer of minus 0.3, okay, if we round off. What would the units on that number be? Okay, well, it comes down to asking yourself, what are our function and our distance being measured in? Our function measures temperature in degrees Celsius, and distance is being measured in centimeters, so we're going to get degrees Celsius per centimeter out of that. Okay, and that number that we just calculated is what's known as a directional derivative. It's our estimate of the directional derivative of t at 1, 1 in the direction of PQ. Okay, that's kind of a lot in that sentence. Okay, but we measured the rate of change in a direction, in a particular direction. That's what we did. Okay, so that's an estimate. What I'd like to do now is to go back and look at the graph. We got that estimate by looking at the contour plot. Okay, we can look at the graph as well. Okay, that's the picture over here to the right. And notice that P and Q are sitting down here. So from P to Q would be going from here to here. And if you kind of follow the points P and Q up to the surface, they would be here and here. And so that minus 0.3 that we just calculated, visually, that would be the slope of this line segment. Okay, rise over run, that gave us our negative rate of change. Okay, but, kind of peeking back down here, notice that's just an approximation. To find the exact rate of change, we would need to think about a tangent line at P. Okay, I'm going to do my best to draw this in. So if we wanted to know what the exact rate of change of the temperature is at P, we would have to draw a tangent line, kind of just rests on the surface, and parallels the direction P and Q. So picture this line. It's kind of resting on the surface and being right above this direction vector from P to Q. I'm going to label that line L. And if we could find the slope of L, that would give us the exact directional derivative. Okay, let's make that as a comment down here. Okay, would be the slope of the line L that we drew in above. Okay, but then the question is, how do we find the slope of that line L? Okay, it turns out there is a nice formula for doing that. Okay, so we'll scroll ahead to the next page here. Okay, take a look at this theorem. So it's going to start us off with an assumption. Let's suppose that u equals u1i plus u2j is a unit vector. Do you remember what that means? A unit vector is just a vector that has length 1. Okay, and then if we have a differentiable function, we can calculate the directional derivative. Here's some notation first. So f sub u, we would read that the directional derivative of f in the direction of u. That's what that symbol means. Okay, and here comes a formula for it. Okay, so we can calculate that directional derivative by taking the partial derivative with respect to x times u1, the first component of our vector, plus the partial derivative with respect to y times the second component. And what's interesting about that quantity that we have, notice that we took the two partial derivatives, those are the components of the gradient vector, and then we multiplied by the two components of our unit vector. And so what we're really looking at here is a dot product of the gradient with this unit vector u. There's a formula that will give you the exact value of a directional derivative. Okay, now there's one very important caution that I want to give you when you're using this formula. In order for this formula to work, you have to have a unit vector. Your u has to be a unit vector, and if you don't have a unit vector, you need to convert whatever vector you have into a unit vector. Okay, so u must be a unit vector. We'll do examples so you can kind of see how all of that works. Okay, and one closing comment. If you're curious about where this formula came from, there is a derivation for it. It doesn't come out of thin air. I'm not going to run through that in this video, but you are welcome to look at my written notes on page 39 if you want to just step through and see where this formula came from.